So as we said earlier, so the lag compensator has some advantages and disadvantages. The lead has some advantages and disadvantages. So what if we can use both? And this is what's called the lag lead compensator, or the lead lag compensator. So in this case, we will combine both compensators at the same time. So this is the pole 0 of the lead compensator, okay, where we have the magnitude of the pole is greater than the magnitude of the 0. And this is the lag compensator in which we place the pole on 0, the magnitude of the pole greater than the magnitude of the 0. So it's the other way around, but we make them close together, as we said in the last lecture, to minimize the effect of the pole. Okay, so we can make it such that we can design our compensator, our combined compensator, which is now composed of 2 poles and 2 zeros, such that the lead compensator can take care, for example, of the transient characteristics and relative stability and phase margin and things like that, while the lag compensator can focus more on the steady state error. And those are usually contradicting characteristics. So those two characteristics are in most cases contradicting together. So it would be nice if we can have something that has the benefit of both. Okay, so this reminds us of something like something similar to when we talk about the PID controller, for example. So when we talked about the PID controller, okay, we were talking that the integrator was like improving the steady state error, but it was adding some instability, while the derivative part was like trying to enhance the transient characteristics and reduce the overshoot. Okay, so they were like working together. So this is like a different way of different architecture, different controller architecture. PID is maybe more famous in the classical control point of view, but this is still lead and lag lead compensators are still also used in the controller as a good controller architecture. Okay, in fact those are not the only ones. Okay, so let's say that we have a compensator, or that we have a system. Okay, let's say that we have a system in which we have those open loopholes, and let's say we're not happy with them, and we want to let's say place our open loopholes in this part. So how can we do that? Okay, so we can simply design a controller or a compensator which tries to add like 2 zeros on top of those 2 poles, and then it has those 2 poles instead. So if we can make a compensator that works like this, so it can simply remove the poles from one and place them on another place, and this doesn't have a particular name, okay, in the literature, but it can be done. The problem is, where is the problem here? The problem is that it's about inaccuracy. So even if you put a 0 right on top of the pole, okay, you're not exactly sure if you're going to cancel it completely. Why is that? The reason is because when we do that, you usually do that with a realistic controller, with actual hardware. So you need perfect hardware to do this, and this is not available, especially when we're talking about analog controllers or analog compensators. Okay, when we move towards digital controllers, things will become maybe a little bit better, but still it's not guaranteed to cancel those poles completely, and this is one reason why it's not always accurate. It's not always accurate. But the point to keep in mind is never, by any means, use this technique to, let's say, for example, cancel a pole in the right half plane. So if you have a pole in the right half plane, and let's say, okay, I'll design a compensator that places a 0 on top of it, this is completely wrong and very, very dangerous. Why shouldn't we do that? The reason is because if this inaccuracy, if it happens here, then yeah, maybe it will work, but it might not work as expected. But if any inaccuracy happens here, this will lead to instability. The system will become unstable, and this is something that we cannot tolerate. So even since you never have perfect hardware, you'll never be able to have perfect op-amp and perfect resistors and perfect capacitors to build your hardware controller. And even if it's a digital controller, your microprocessor is not going to be perfect. There's always going to be unexpected delays and unexpected errors, as we will talk in the digital control part. So you should never do this in order to stabilize an unstable system or to cancel out a pole at right half plane. If you want to do that, then you better use other methods. For example, you try to use root locus, you try to use other methods, but you don't try to cancel the pole by directly placing a 0 on top of it. This is completely wrong and it should not be done.